presentation on energy accounting. So first of all, why should this matter to you? How can you benefit from understanding your utility bills and your utility usage? So first of all, understanding the details of your utility bills can help you understand the real operating costs of equipment or a process. Also, per unit energy costs can change over time, leading to variations in total energy costs. By recording and tracking the amount of electricity, natural gas, and other types of energy you use, you can identify any unusual levels of usage. So unexpected changes in the usage can be a sign of a problem. So if your natural gas usage increases and there's no reason why that you can come up with, there's a chance you may have a leak. If electricity usage is increased for no apparent reason, that could be due to faulty equipment. So by catching these problems early, we can limit losses and potentially avoid interruptions in production at our facilities. And without understanding the usage, just paying the bill when it comes each month, these problems can linger, driving up costs unnecessarily. And finally, when exploring opportunities to improve energy efficiency and reduce costs in your facility, you must know the amount of energy saved and the value of that energy to determine a payback period for the project. Without being able to estimate a payback period for a project, it can be difficult to justify undertaking the project. And by understanding how you're billed for energy, economic calculations can be more accurate, and you can be more confident in the estimated cost savings. So over the next hour or so, we'll first discuss some basic energy concepts and some fundamentals of electricity. Understanding these concepts will make it easier to understand the later topics we discuss. After that, we'll briefly discuss the electrical grid and how electricity is generated and distributed. After that, we'll take a deep dive into electricity billing. Electricity billing is generally not very straightforward. A lot of people just pay what's owed and ignore the rest of the billing statement, and that's understandable. If you've ever really dug into an electricity bill, even a statement from your own home, you know that it can be sort of confusing. And I'll help you understand the different components of your billing statement and some ways you can take advantage of that understanding. And finally, we'll wrap up the presentation with a brief discussion of natural gas and other fuels that are used in industry. So first, let's talk about some basic concepts of energy. So some of the most common industrial energy sources are electricity. Electricity is used in just about every facility, and it comprises about 29% of industrial energy usage. Biomass, which involves the combustion of wood products, agricultural waste, or other organic matter to generate energy, comprises about 8% of energy usage in industry. Currently, though, the majority of energy used in industry comes from fossil fuels, primarily natural gas and petroleum products such as gasoline, diesel fuel, propane, kerosene, and so forth. So while the focus of our discussion today will be electricity, natural gas and petroleum products will also be briefly discussed. So first, the British thermal unit. The British thermal unit is a unit of measure commonly used when discussing energy. The BTU is handy because it's a standard unit that can be converted to and from other units of energy. We can convert units of electricity usage, natural gas usage, and other fuel usage all into British thermal units. A British thermal unit, or BTU, is the amount of heat that's required to increase the temperature of 1 pound of water by 1 degree Fahrenheit. It's equivalent to about 1,050 to 1,060 joules of energy, depending on the initial temperature of the water. So as we discuss the different energy types today, I'll mention the BTU equivalents of each. So first, we'll talk about electricity. So electricity is a type of energy that involves the flow of electrons along a conductor, such as wire or other metals. Electricity is what's known as a secondary energy source, and that means that electricity is created from other energy sources. Electricity, while naturally occurring in like lightning and things like that, it doesn't present itself in a way that we can collect and utilize it. So all the electricity that's used um, productively is created from a primary energy source. So heat from the sun can be converted to electricity. Petroleum-based fuels can be used to generate electricity. Nuclear energy can be used to generate electricity. And as I mentioned, electricity is widely used across industry. You'd be hard pressed to find an industrial facility that doesn't use electricity in one way or the other, and usually in significant amounts. So lights are all powered by electricity. Electricity is necessary for cooling and for ventilation purposes. It's often used in heating. Aside from heat generation, process equipment is usually powered by electricity. Air compressors and other pneumatic equipment ultimately powered by electricity. Motors and pumps, computers, office equipment, control panels, all powered by electricity. So let's look at some of the fundamentals of electricity. So first, to fully understand electricity and electricity billing, a basic knowledge of the fundamentals of electricity is helpful. So first, we'll look at voltage. And voltage is the force that pushes electricity through a conductor and to your device. And it's measured in units of watts. And the voltage is ultimately determined by the source of the electricity. So if we're using cylindrical batteries like double A's or triple A's, the kind you find in your remote control for your TV, those batteries provide electricity at 1.5 volts to the devices that they're powering. The battery in your car will provide about 12 volts of electricity to the electronic components in your car. And all those components in your car are designed to run at that 12 volts. Now, the wall outlets in your home that you use to power your television, your computer, small kitchen appliances, phone chargers, and so on, they provide electricity at 120 volts in the United States. Some of the bigger, more energy intensive appliances in your home, such as your dryer, your hot water heater, your HVAC unit, those will usually require 230 volts. And industrial equipment often has that requirement as well. And some large industrial equipment can even go up to 480 volts, sometimes beyond. So higher voltage means that the electricity is pushed through faster, but that means that electricity is being used quicker as well. So these higher voltage equipment usually have higher operating costs. Next is current. And current is how much electricity can pass through the conductor at one time. So if we look at the cross section of a wire that's carrying an electrical current, the current is how much can pass through that cross section, is passing through that cross section. And the current is given in units of amperes or amps and abbreviated with the capital letter A. Now, resistance slows the flow of electricity through a conductor, and it's given in units of ohms, noted by the capital omega. So since electricity is invisible, it can be difficult to sort of conceptualize how it moves. So it can be easier to understand electricity by comparing it to water. Water and electricity act somewhat similarly, but they have different driving forces. So for a moment, let's think of electricity as water, and let's briefly look at what we call the water hose analogy. So in this scenario, the water hose would be the conductor. Once a water hose is hooked to a water source, the water will begin to flow through the hose, and the rate that it flows through will depend largely on the water pressure from the water source. So the water pressure is analogous to the voltage pushing the electricity along the conductor. When the water pressure is increased, water flows faster through the hose. The same is true with electricity. As voltage increases, the amount of electricity moving through the conductor increases. So if we increase the diameter, or rather the cross-sectional area of the water hose, and we keep the water pressure the same, the amount of water that moves through the water hose will increase. If we make the hose smaller, the amount of water that passes through will decrease. This is similar to the current. As the current increases, the flow of electricity increases. And finally, resistance slows the flow of electricity. This would be like a blockage or a kink in the water hose. So hopefully being able to visualize these concepts will help make them clearer for you. So as you might imagine from the water hose analogy, there's a relationship between voltage, current, and resistance. Voltage, current, and resistance are interconnected through Ohm's law, which states that the current flowing through a conductor between 2 points is directly proportional to the voltage across the 2 points and inversely proportional to the resistance of the conductor. Mathematically, this relationship is expressed as V equals I times R, or voltage equals current times resistance. This is a very important concept, especially when designing electronics. It's not going to be incredibly crucial to understand in depth for your electricity bills, but if you dive deeper and begin considering changes to your facility and to your processes or equipment, this can come in handy. So more importantly to our objective in this presentation is wattage. And watts are a unit of power equivalent to 1 joule per second. And watts represent the rate at which a device uses electricity. So if a device uses 100 joules of energy per second, it'll use electricity at a rate of 100 watts. So this really begins to help us understand how much electricity a device is actually using. You'll see watts labeled on light bulbs. And when looking at the same type of bulb, a higher wattage bulb will use more electricity, but will also provide more light generation. You'll also see speakers and audio equipment labeled with the wattage that they can safely use. So speakers with a higher wattage will be louder. Computer power supplies, when sold as components, are labeled with the wattage they can provide to the other components in the computer. Some other consumer goods will include watts, but many won't. And this is in part because the electricity used by a product will largely depend on the load on the product. And industrial equipment specifically doesn't often include the wattage on the label, since the electric draw of the equipment is highly variable depending on the load of the equipment. So most industrial equipment and many home devices will instead be labeled with their current, usually the peak current that they can draw. Fortunately, a relationship exists between watts, voltage, and current. So watts is equal to the volts times the current. And since the voltage that's being supplied to a device is usually known, we can use that with the current to calculate the watts. So if we have a device that plugs into a standard wall outlet that provides 120 volts and the input is 0.2 amps, the device will use electricity at a rate of 24 watts. But watts are a small unit. It's easy to use a lot of watts. So when we're looking at the electricity use of a facility, it makes more sense to use kilowatts. And a kilowatt is equal to 1,000 watts. So if we have 10 light bulbs that are 100 watts each and they're all running at once, the rate of electricity used for these light bulbs would be 1 kilowatt. So this instantaneous rate of electricity usage is often referred to as the demand, i.e., in other words, the demand to run these 10 100-watt lights is 1 kilowatt. So as we mentioned in the previous slides, watts and kilowatts are units of power representing the rate of electricity usage. Kilowatt hours, on the other hand, is a unit of energy. It represents how much energy is actually used by a device, a system, or a facility. This is often referred to as usage or consumption. As the name suggests, kilowatt hours are a product of the rate of electricity use in kilowatts and the amount of time in hours that rate of electricity is being used. So for instance, if we have 10 lights that are 100 watts each, and we run them for 1 hour, 1 kilowatt hour of electricity will be used. 100 watts times 10 times 1 hour is 1. Now, if we run those same lights for only a half an hour instead of an hour, we'll only use 0.5 kilowatt hours or 500 watt hours of electricity. On the other hand, if we have 5 lights that are 50 watts each, we can run them for 4 hours until we'll use 1 kilowatt of electricity. And likewise, running those 10 lights that are 50 watts each for 4 hours, running all 10 lights that are 50 watts each for 4 hours, we use 2 kilowatts hours of electricity. And a kilowatt hour is equivalent to 3,412 BTU. So the graphic that's up on the screen now helps understand the relationship between usage and demand over the period of a day. The higher the demand is at any one time, the faster that electricity is being used. Demand is usually lowest when the facility is not operating, with increased demand during operating hours. The peak demand occurs when the most energy is being used. Business and industrial consumers can lower electricity costs both by lowering their peak demand or lowering their usage, and we'll see why shortly. But first, we'll briefly discuss how electricity is generated and distributed to the consumer. The electrical grid is an interconnected system that's used to deliver electricity from electricity producers like power plants to the consumers. And in the US, there are 3 major grid regions. That's the Eastern region, the Western region, and the Texas region. The Eastern and Western regions are each comprised of multiple subregions, and there's interconnection within and between these subregions, which provides redundancy to help minimize loss of local power. So if one subregion, the grid of one subregion is having issues providing the power needed, other interconnected subregions can help make up those losses. The map on the screen shows the different electrical grid subregions across the contiguous United States. Within each of these subregions are many power plants that generate electricity from primary energy sources and send it into the electrical grid. There are differences in the breakdown of energy sources used to generate electricity from power plant to power plant, locality to locality, and subregion to subregion. This means that the electricity rates and environmental impact will vary from place to place. The EPA maintains information on the electrical grid, including the breakdown of energy sources, the amount of electricity generated, and the environmental impact of each power plant in the country. And the hashed lines in the map indicate interconnection between adjacent subregions. So the most common energy sources for electricity generation are natural gas, coal, nuclear, and renewables. The graphs on the screen show how much each of the energy sources contribute to electricity generation in the RFCW region, which includes most of West Virginia, Ohio, and Indiana. And this is my local electric subregion. This also shows how the RFCW subregion compares to the national averages. In this subregion, coal and nuclear power are relied on much more heavily for electricity generation than across the nation on average. And natural gas is used slightly less, and renewables are used significantly less in this subregion. This also plays a significant role in the environmental impact of power generation in each subregion. Generating electricity from nuclear sources creates no carbon dioxide emissions. Renewable sources also have a lower environmental impact from an emissions perspective. While electricity generated from natural gas has significant emissions, and coal has about double the emissions of natural gas. So the electricity in the power plant is usually generated at a relatively low voltage, at least by electrical grid standards. So we're looking at around 2,300 volts to 30,000 volts. Now, the electricity that's generated by the power plants is then sent through transformers. And these transformers are used to alter the voltage. In this case, we're first increasing the voltage to anywhere from 115,000 volts up to 765,000 volts. Stepping up the voltage allows the electricity to be transmitted more quickly across the electrical grid. Once the transformers increase the voltage, the electricity is transmitted across the subregion with transmission lines. And at the destination, the electricity passes through one or more transformers, which step down the voltage to the level needed by the consumer. And that's going to be different for a residential consumer and a large industrial consumer. A residential consumer would generally only need access to 120 and 230 volts, where industrial facilities can sometimes require much higher than that. So now that we've discussed some fundamental concepts of energy and electricity, and we've looked at how electricity is generated and distributed, let's look at electricity billing. So to fully understand your utility bills, you'll have to look at the tariffs. So tariffs, when discussing electricity bills, refer to a document created by the electric company that details how the consumer is charged for their electric usage. The electricity companies are regulated by the Public Service Commission, and this means that these companies can't unilaterally change their rates. So for a rate change or any other change to the tariffs to be allowed, it has to be approved first by the Public Service Commission. And as part of the regulations, the companies must make these tariffs available to consumers. Usually the most recent tariffs are available on the website of the electric company, but some companies do make it more difficult to obtain the tariffs. Some will want you to come into the office to get copies. Some will want to mail them out, so forth. So one thing to note is that the tariffs that are outdated are almost impossible to find. You'll also see shortly that each page in the tariff usually has an issue date and an effective date or both, usually at the bottom of the page, that indicates when the terms on that page were issued and went into effect. Some sections will remain unchanged for a long time, while other sections will be updated much more frequently. The frequency and scope of changes varies greatly. So if you want to be able to replicate the calculations of your bills, you'll need to be sure that the tariffs you're using are all effective for the billing cycle of interest. Also, if changes become effective in the middle of a billing cycle, the cost will be weighted by the number of days at each effective rate. Now, electricity companies can offer different types of services depending on the type of facility, the electricity usage and demand, and the voltage needs. And these different services are called rate schedules. So rate schedules will vary between companies, but they'll usually include categories such as residential, churches or places of worship, schools, general service for small business and for businesses and small industrial facilities, large industrial, and other services such as outdoor lighting and so forth. So each of these use cases has different usage patterns and electricity demands and requirements. So your rate schedule can be found on your billing statement, but it's not always very clear. So let's look at a couple of examples here. So first, the QR codes on the screen, I've provided links to 2 tariffs from 2 of the electric companies located in West Virginia, Mon Power and Appalachian Power. Please take a moment to download and open these up in a PDF viewer such as Adobe Acrobat or similar. You can either use the QR codes on the screen or the links that Farzana will be pasting in the chat here momentarily. Can you please post those links, Farzana?
Yes, Dr. Moore, just a second.
So I'll give you a few minutes, or a few moments when she posts the links to download the tariffs so that you can sort of follow along while we're working through this. And one thing that you'll notice once you look at these tariffs is that while there are differences, in the grand scheme of things, they're actually pretty similar. So Farzana's posted the links to the most recent Mon Power and Appalachian Power tariffs in the chat. So if you want to take a moment and download those, we'll begin looking at them. So while you're working on downloading those, let's first look at this billing statement, or this part of a billing statement from Mon Power. And let's look at the highlighted line from the billing statement. This line is labeled as rate, and it's the information provided is general service MP-GSCF. So this information here actually tells us exactly which rate schedule we're going to be on. So let's remember that, general service MP-GSCF. So if we go to the second page of the Mon Power tariffs, this is part of what you'll see. This is the index. This is called the index of schedules in the Mon Power tariffs. Now I've cut this down to only include the different rate schedules. There are also sections before and after these that have a lot more information regarding the billing of electricity. So in the code that we found on the billing statement, that MP-GSCF, the MP first stands for Mon Power. So Mon Power is part of a larger corporation that has that oversees several energy companies. So this keeps their this is specific to Mon Power rate schedules. Now the next 2 letters indicate the usage category, and in this case, that's going to be general service, the GX. So if we look at the rate schedules, we see three general service schedules: general service schedule B, C, and D. So the next letter following the usage category will indicate the exact schedule. In this case, the C after the GS indicates that we're going to be using general service schedule C. So if we go to section 9.1 in the non-power tariffs, we'll see the tariffs for the rate schedule of the account on the statement. So general service rate schedule C. So now with the non-power, we've found out how we can identify our rate schedule. Appalachian Power, on the other hand, handles it a little bit differently. And the rate schedule is provided in the highlighted line. And in this case, it says Tariff 261 General Service. So let's see if we can identify the specific rate schedule here. So again, if we open the Appalachian Power tariffs, and we turn to the index located near the beginning of the tariffs, we'll find the following rate schedules listed. So there is a rate schedule that's named General Service. So that looks like a good place to start, since our rate schedule was Tariff 261 General Service. So we'll move to section 11.1 through 11.4 in the rate tariffs. And in this case, the general service schedule has information for four different schedules, and they're numbered 261, 263, 265, and 267. So recall that the rate schedule listed in the billing statement was Tariff 261. So now we found our rate schedule, the highlighted schedule code 261, and it begins with this highlighted line. So as you explore the rate tariffs for your electric company, the rate schedule may be provided differently in the billing statement, but it will be there in some fashion. So a good approach to figuring this out is to begin by looking at the tariffs to see which rate schedules are available and how they're labeled. And that can give you a better idea of what you should be looking for on the billing statement itself. Now, if all else fails and you can't find your rate schedule, the electric company should be able to help you, should be able to provide you with that information. So giving them a quick call and asking is another way to figure out your rate schedule. So now that we know how to use the bills to find the rate schedule, let's explore the different components that influence electricity costs. And broadly, there are five main components of electricity billing, and those are customer charges, usage charge, demand charge, other charges, and taxes. So let's look at each of these more deeply and see how they can affect the total cost of your electricity service. First, every rate schedule will include a customer charge. A customer charge can also be referred to as a service charge or a basic service charge, or under some other different names. But generally, this is a monthly flat fee that's charged to the customer, and it's going to vary between the different rate schedules. So while the customer charges vary between companies and rate schedules, the typical ranges tend to be in these neighborhoods. So for a residential account, you're looking at a customer charge of about $5 to $20, depending on the area. For general service rate schedules, you're looking at about $30 to $50 a month. And for large industrial, it can be upwards of $100 to $200 per month. And these fees just support the basic maintenance of the account, billing, customer service, and so forth. So here's some examples of how the customer charges are shown in the Appalachian Power and the Mon Power rate tariffs. So Appalachian Power refers to it as a basic service charge. And for the 261 rate schedule, it's $35 a month. Mon Power just calls it a customer charge, $46 per month in this tariff. So regardless of your usage levels, this charge is always going to be there. Even if you don't use any electricity somehow for a month, you're still going to be charged a base rate at least. So one major component of electricity costs are the usage charges. And usage is charged on a per kilowatt hour basis. The usage cost per kilowatt hour varies by rate schedule and can be organized or structured in several different ways. So some usage charges will be a flat rate per unit. So flat rate usage charges will charge a certain amount per kilowatt hour used, with each kilowatt hour costing the same regardless of how much your total use is. Usage charges may also be tiered. When usage charges have a tiered structure, the price per kilowatt hour will change at certain thresholds. They can also be structured seasonally, such that the cost per kilowatt hour will depend on the month of the year. And some rate schedules will charge a different amount for usage at different times of the day. This is called on-peak and off-peak billing. On-peak and off-peak times will be defined in the tariffs, but typically the daytime hours when electricity usage is typically the highest is considered on-peak, while nighttime hours are typically off-peak. So usage rates are lower during off-peak to encourage consumers to move their energy use to off-peak times when the electrical grid is not as strict. And to complicate matters even more, sometimes combinations of these structures are used. So let's look at a couple examples. Tariff 261 rate schedule from Appalachian Power includes a tiered usage rate that depends on the billed demand, where the first 350 kilowatt hours per kilowatt of demand is charged at 2.534 cents per kilowatt hour, while usage beyond that threshold is at a lower rate of 0.866 cents per kilowatt hour. So facilities under rate schedules like this can benefit greatly by reducing demand. So for example, if peak demand during a billing period is 20 kilowatts, the first 7,000 kilowatt hours used will cost the higher rate. So the first 7,000 when the demand is 20 kilowatts. Now, if we can reduce that peak demand to 10 kilowatts and we maintain the same kilowatt hour usage, only the first 3,500 kilowatt hours is charged at that higher rate. So you're not only saving money on the demand, as you'll see, but you're saving money on those kilowatt hours as well. Now, on the other hand, the energy charge from the Mon Power tariff on this rate schedule on the screen, that's just a flat 5.557 cents per kilowatt hour, regardless of the amount of usage. So here's an example of a tiered structure. So this is found in the residential rate schedule of Appalachian Power. It also includes, though, a seasonal element. So in this rate schedule, regardless of the month, the first 500 kilowatt hours and the subsequent 850 kilowatt hours until we get up to this 1350 value will be at the rates of 8.558 and 7.20 cents respectively. Now, during the winter months only, so January, February, and December, the usage beyond that first 1,350 kilowatt hours is going to be charged at a reduced rate of 4.144 cents per kilowatt hour. And the idea behind this is to generally help ease winter energy costs for residential consumers. This rate schedule is from Appalachian Power, and it includes an on-peak and an off-peak component. So when an on-peak, off-peak rate structure is used, the on-peak and off-peak time periods must be defined. In this case, we can see that the off-peak energy costs are significantly lower than the on-peak energy costs. Facilities that have this type of rate structure and operate mainly during on-peak hours may benefit from switching some or all production hours to the off-peak time periods. In this case, operating during off-peak hours could cut the usage charge by nearly 80%. While operating during off-peak hours can have challenges, the opportunity to cut costs may make it an option worth exploring. So along with the usage charge, which is based on the kilowatt hour usage over the billing period, the demand charge also represents a large portion of electricity costs, especially for industrial facilities. Residential rate schedules are much less likely to contain a charge based on demand. However, residential rate schedules usually stipulate that a demand meter can be placed if demand is higher than normal. So recall that demand is the rate of energy usage, and that's specified in kilowatts. Demand charges are based on the peak demand sustained over a 15-minute period during the billing period. So like the usage charge, demand charges can be flat rate, tiered, seasonal, or on peak and off peak. So let's look at some examples of these demand charges within the rate schedules. So both of these schedules include demand charges. The Appalachian Power rate schedule has an on-peak, off-peak structure where demand used during off-peak hours is charged at a lower rate. So Appalachian Power, as you can see, provides a lot of incentives for consumers under this rate schedule to modify and reduce their demand. So reducing the peak demand, not only lowers the demand charge, but it also reduces the per kilowatt hour use by lowering the threshold where the per kilowatt hour charge lowers. So shifting high demand use to off-peak hours can reduce the demand charge by a significant amount. Consumers under Mon Power's General Service Schedule C, on the other hand, are again just charged a flat rate per kilowatt of peak demand, regardless of how small or large their demand is. On the other hand, Mon Power's General Service Schedule D include the following charges, which is include a tiered demand charge. So this is a rate schedule that's more appropriate for a large industrial facility with high energy needs. And in this case, the first 500 kilowatt of demand are charged at a lower rate than additional kilowatt over 500 kilowatts. So along with the base demand charges, ratchet clauses and power factor penalties are also related to the demand of your facility and can increase your electricity costs significantly. So first we'll discuss ratchet clauses. Total electricity use across the US varies significantly throughout the year. So during the summer months, electricity demands tend to be higher than other times of the year because everyone's running their air conditioners trying to stay cool. And that's a lot of extra energy used to just maintain a comfortable environment. But the electrical grid needs to have the capacity to provide all this extra power, to power all these air conditioners at the same time, in addition to the usual demand. And that requires building and maintaining a lot of expensive infrastructure to generate and supply that energy. That means that for most of the year, the capacity of the electrical grid is significantly higher than the needs, which means that the power companies will have the same expenses year round, but the revenue will decrease during those times of year. So ratchet clauses were designed to avoid these shortfalls by penalizing businesses that have a peak demand that is significantly higher some months of the year than others. So let's see how that works. In the Mon Power and Appalachian Power tariffs, there aren't ratchet clauses, but I was able to find one from an energy company that's not local to me. And that ratchet clause is highlighted in the picture. It states, the demand shall be measured at 15-minute intervals and for billing purposes shall be the greater of 1, the maximum demand occurring during the month, or 2, and this is the ratchet clause, 75% of the highest demand during any of the preceding 11 months. So let's see how a ratchet clause like this can drive up costs. We'll use an example scenario here. So let's assume that these values are the monthly peak demand for a facility over a 2-year period, 2022 and 2023. In most months, as you can see, the demand is between 8 and 12 kilowatts. But let's assume that in December of 2022, something drove the demand up significantly, resulting in a peak demand of 40 kilowatts. So here's a graph of that data. It shows a peak of 40 kilowatts during December. Without a ratchet clause, this would be the basis of the demand charges for each month. Now let's see what happens with that ratchet clause. Recall that it stated that the billed demand would be 75% of the highest demand during any of the preceding 11 months. So this peak that occurs in December causes this to happen. So now the ratchet clause is going to drive the cost much more. So from January of 2023 to November of 2023, that 75% of the highest demand in the preceding 11 months, that's 30 kilowatts. And it's higher than the actual demand each month. That means that for those 11 months following December 2022, you'll be billed for 30 kilowatts of demand each month instead of the actual demand ranging from 8 to 12 kilowatts. So let's assume that this business is paying a demand rate of $15 per kilowatt. And let's look at the demand charges over this 2-year period with and without the ratchet clause. So this table is separated into 2 sections to represent the demand charges based on the demand rate only and the costs with the ratchet clause applied. So the values that you see in green in the base demand rate only and in red in the with ratchet clause sections are the costs that were affected by the ratchet clause. So the ratchet clause resulted in much higher electricity costs in 2023 than if there was no ratchet clause and the demand was charged at a flat rate. So if we look at those numbers a little more closely, the 2023 demand charges would increase from $1,950 to $5,130 in this scenario. That's a difference of $3,180, or an increase of 163% over the base demand rate only. So see, this is some serious incentive to keep your demand rate under control. If you're facing ratchet clauses, they could be driving up your costs tremendously. And the solution could be something as easy as cascading equipment instead of using it all at once, or just more careful planning of your process, or replacement of high usage equipment with more efficient equipment that has a lower demand. So power factor is another concept that's related to demand and can play a role in electricity costs. The power factor measures how effectively electrical power is utilized to do work. It's a ratio of the real power in watts to apparent power in volt amperes. And the power factor takes a value between 0 and 1, representing the proportion of electrical power that's converted to useful work. So for example, a power factor of 0.75 means that 75% of the electric is utilized for useful work, and 25% of it is essentially wasted. So a power factor equal to 1 means that all power is effectively used for work. And this only happens for purely resistive loads, things that sort of act as heating elements. So incandescent light bulbs, toasters, space heaters, and so forth. Now, the power factor for a facility is usually less than 1. A power factor of less than 1 indicates the presence of reactive power, which leads to inefficiency. And this is caused by inductive or capacitive loads, such as electric motors, transformers, compressors, speakers, ballasts, and so forth. So let's go back to our example of a power factor of 0.75, meaning that 75% of the electricity is used to perform useful work, while the other 25% of the electricity is wasted power. So as a note, you'll see that we're now referring to build demand in kilovolt amps. So when power factor is equal to 1, kilovolt amps is equivalent to kilowatts. But when the power factor is less than 1, kilovolt amps is a combination of the useful power in kilowatts and the wasted power in kilovars. And kilovars are kilowatt amps of resistive power. And often, electricity companies will have clauses in the tariffs that penalize industrial facilities if their power factor drops too low. So here's an example of power factor penalties in Mon Power's Schedule D general service and from the Appalachian Power tariffs at the bottom. So let's see how each of these cases increase cost. So Mon Power's power factor penalty, it penalizes industrial consumers under this rate schedule when the reactive power demand exceeds 35% of the built demand, and that means a power factor of 0.65 or less will be penalized. So if the built demand is 1,000 kilowatts, and that includes 500 kilovar of wasted energy, in other words, we're talking about a power factor of 0.5. The power factor penalty would be for those 150 kilovar at 40 cents each, or an increase in electricity costs of about $60. So Appalachian Power's power factor penalty is worded slightly different, but it works very similar by imposing costs when the power factor drops below 0.5. So if power factor penalties are driving up your electricity costs, capacitors can be used strategically in line before equipment or in the power system in the building to correct the power factor and reduce the power factor penalty. The final major component of most of these rate schedules is a section of other charges. And every rate schedule that I've seen has this. And these are charges that are applied to the bill, and they're usually to recover other costs aside from generation and distribution of service. Occasionally, there will be credits included in this section as well. And these charges exist on rate schedules of all types, even residential service. These charges are usually based on either per kilowatt hour usage, per kilowatt hour demand, or sometimes both. And they can add a substantial amount to the total cost of your electricity bill. Some examples of these other charges are vegetation management surcharge, which helps recover the cost of trimming or removing trees and other vegetation around the transmission and distribution lines and other electrical grid infrastructure. There's usually one or more environmental control charges to help recover costs of minimizing environmental impact. There's sometimes renewable electricity surcharges to help recover losses from consumers turning to renewable energy systems, and more. So let's look at a couple of these. Now here are the examples from rate schedule from each tariff. Instead of detailing each of these surcharges within the rate schedule, each of these charges points to a different sheet in the tariff that provides the rate structure for each charge. The Appalachian Power Tariff, the one on the top, uses abbreviations to refer to each of these additional charges. So let's look at a few of these charges from the Mon-Power tariffs. And I've highlighted two of them specifically. First, we'll look at the environmental control charge, and it points to sheet 6B1 in the Mon-Power tariffs. So if you move to that page in the Mon-Power tariffs, you'll see a table that looks like the one on the left. As you can see, the actual cost of these charges depends on the rate schedule. For some rate schedules, there's only a fee based on demand, while other rate schedules will have a fee based on both demand and usage over the billing period. For the case of General Service Schedule C, there's a 43-cent per kilowatt charge, along with an additional charge of 0.14 cents per kilowatt hour, as highlighted in yellow. Now, on the other hand, for this rate schedule, the environmental control charge normalization fee credits users based on their demand and usage. In accounting shorthand, the parentheses or brackets around the values indicate a negative value. While this charge is a credit for some rate schedules, for other rate schedules, it becomes a fee. So if we look at the AGS rate schedule, the normalization, the environmental control charge normalization increases their cost per kilowatt and their cost per kilowatt hour significantly. While for rate schedule C, it actually is a credit, a small credit. Oops, sorry. So in this table, all the other charges that apply to the Mon-Power General Service Schedule C were identified and tallied. And as you can see, these additional charges can add up. This is one area where a deeper understanding of the tariffs can help you make more informed decisions. So let's assume that we're considering replacing an outdated piece of equipment that has a full load demand of 50 kilowatts, and we want to replace that with a more efficient unit with a demand of only 30 kilowatts. Without considering these other charges, you'd expect each kilowatt of demand reduction to save about $17.04. That's what the demand rate is, right? But considering these other charges, we can see that we would really save $20.50 per kilowatt of demand reduction. So when we're performing return on investment calculations using the base demand rate instead of the actual demand rate, that could lead to the decision to not undertake a project that would meet the ROI requirements for the business if the actual demand rate was considered. And we can see from this chart here that these other charges increase represent an increase from the base demand rate and base usage rate of 16.9% for the demand rate and an increase of 2.7% for the kilowatt hour rate. And this is just for this one rate schedule. For other rate schedules, the impact of these other charges is going to be different. And finally, after all those other components are considered and tallied, municipal and local taxes are applied to the bill. In the tariffs, usually near the beginning, you'll find a table listing all the municipalities served by that electric company. Municipalities can have local taxes, municipal taxes, or both. If you're served by the electric company and your municipality is not listed, then that means there are no additional local or municipal taxes applied to your bill. So your bill is going to be based completely on your customer charge, usage, demand, including the power factor and ratchet clause penalties, and your other charges. So after you locate the proper tariffs, identify the rate schedule for your account, and understand the terms of the rate schedule, you need to know where to find the usage and demand information on your statements. And some of these statements make it very clear. Kilowatt hour used is your usage, and billed load, in this case, is your peak demand. Applying the actual demand and usage rates after consideration of the other charges, the customer charge, and any other taxes, that should bring you up to your final bill amount. For consumers with higher usage and demand, meters with multipliers may be used. The multiplier is going to be listed in the billing statement, and it's also going to be labeled on the meter itself. So for this consumer, the meter has a multiplier of 192. That means that each 1 unit increase on the meter reading represents 192 kilowatt hours of actual usage. And similarly, an increase of 1 unit of demand on the meter corresponds with an actual demand of 192 kilowatts. So in this case, we can see the difference from the meter is 79 kilowatt hours. And if we multiply that by 192, we get that 15,168 kilowatt hours metered. And likewise, if we take the metered load in kilowatts, 0.254, and multiply it by 192, we get the billed load in kilowatts of 48.8. Now for customers with on-peak and off-peak structures or power factor penalties, the on-peak and off-peak values will be listed and the reactive demand will be provided in some manner. In this case, we have 133 kilobars of reactive demand that's going to increase the cost for this customer. Appalachian Power uses a different layout in their billing statements with usage, demand, and leading and lagging reactive demand when appropriate, listed in a table. And in this case, the meter uses a multiplier of 384 for all readings. So as you can see, the electricity companies do provide all the information needed to understand and calculate your bill, but each company has a slightly different way of handling things. And I hope that by showing you some of the ins and outs of electricity billing, that you'll be able to pick up a billing statement, locate the tariffs, and begin understanding the billing for your facility more completely. Now, very briefly, we'll just discuss natural gas and other fuels. Natural gas is a naturally occurring mixture of hydrocarbon gases, primarily methane. And natural gas is measured in either MCF, millions of cubic feet, or in MMBTUs, millions of BTUs. When we're talking about natural gas billing, we're usually going to see that in MCF, since the volume is going to be consistent, while the energy capacity of natural gas, as we mentioned earlier, can vary. Now, when we're talking about the energy capacity of natural gas, when we're dealing with energy management, we'll often use terms of million BTUs because, as mentioned at the beginning of the presentation, working with BTUs makes a conversion between different energy types much more straightforward. And the energy content of natural gas can range from 1,030 to 1,055 BTU per cubic foot. And that's going to depend on the exact composition of the gas. Natural gas billing, it's much more straightforward than electricity. And it's generally based only on how much gas was used. But natural gas rates, like the electricity tariffs, can change fairly frequently. So from this natural gas billing statement, you can see that the billing is much more straightforward. The present and previous meter readings are given, which is used to calculate the usage in millions of cubic feet. And the cost per MCF was clearly stated. And the bill is comprised only of this usage cost and a customer charge. So it's very easy to see about how much you can save when you save some amount of natural gas. And finally, petroleum-based fuels such as gasoline, diesel fuel, kerosene, and propane are another major energy source in industry. But instead of being delivered by the electrical grid like electric or by permanent pipelines like natural gas, these fuels are delivered as needed and are usually stored on site in large tanks. And the consumers are billed on delivery. So when they call the supplier will come, fill up their tank, and we'll invoice them for it. But this means the usage of these fuels is harder to quantify over a short period. It's easier to quantify these over longer periods, so years instead of months. And to best track the usage, it's recommended to have deliveries scheduled routinely instead of only when the tank is close to empty. So for instance, if you have your tanks replenished every 3 months, it's going to be much easier to estimate how much was used on average each month and how fuel use changes throughout the year than if the refills are sporadic or not on set intervals. And like natural gas, billing for these services is fairly simple, usually consisting of a cost per unit, the volume replenished, and a delivery charge. And depending on the fuel, the BTU equivalent of a gallon of each can range from 90,000 BTU to over 137,000 BTU per gallon for diesel fuel. So that's all that I have for my presentation.